Greetings, this is the scientist and welcome to my digital electronic lab. Let me give you a overview to the different areas of the lab. The first section of the lab is the instrument panel. Any instrument that exists in the real world in any electronic laboratory is here within the instrument panel. The first one we have is a multimeter, a digital multimeter that is used to measure amperage, voltage, resistance, and decibels. The second instrument is a function generator used to generate test tones anywhere within the audio frequency up to RF all the way up to gigahertz, which is in the satellite frequency range. Next, we have a watt meter that is used to measure watts from a audio amplifier or a transmitter, radio transmitter. We have a 4-channel oscilloscope used to monitor the different areas of the circuit. We have a baud plotter used to measure frequency response of the instrument. The next section is the parts bin, where there's over 20,000 parts in the parts bin, and just about any part that you could go and buy from the electronic store, you can find them here. We have hundreds of resistors with different values, capacitors, op amp have different values, and whatever that is not in the part bin can be constructed from what we call SPICE models. I've extracted some parts from the parts bin to design this microphone preamp that I already laid out on the board. The heart of the API microphone preamp is the 2520 op amp that was designed from a SPICE model, and this is 100% of what you'd get in the real world. The second part of the API microphone preamp is the input and output transformer. So I'm going to start by wiring up the transformer. If you notice on the transformer here, you'll see these two dots, and what these two dots represent the start and the finishing winding of the transformer. The start winding of the transformer is the positive terminal of the transformer. The unmarked terminal of the transformer is the ground terminal, which I'm going to connect to ground. Then for the output transformer is the same thing. The mark here, the dot you have right here, is representing the start of the transformer, which is also the positive side of the transformer. That's going to the output of the op amp. Then the finishing winding of the transformer is what goes to ground, and I'm grounding it to the op amp. And then the output of the transformer also goes to ground. Going to change this ground wire to a green so we recognize ground. The second part that we're going to hook up here is the power supply to the op amp, which is going to the positive lead of the power supply. And the negative lead is going to the negative side, which is the minus side of the op amp. Go ahead and change this to a different color so we can easily recognize Next, I'm going to go to the feedback section of the op amp, and I'm going to be putting a 20k ohm resistor that I took from the part bin from the feedback section, 20k ohm from the feedback to the inverting side of the op amp, which is the negative side of the op amp. The op amp have two input. We have the inverting side of the op amp, which is the negative side, and the non-inverting side of the op amp, which is the positive side. Um, Next, we're going to hook up that trim or the gain control that you would have on the preamp. I put the 71 ohms resistor here as a limiter resistor, so when I reach max on the gain control, the preamp won't go into clip. Then I'm going to ground this side of the trim or the gain control to ground through this capacitor. And the reason for this capacitor is to block any DC voltage that would get inside the op amp. The op amp do not want to see DC voltage. The next part of the op amp going to be wired up is going to be the phase switch. This switch is what you would press on a console if a instrument was out of phase. I'm going to wire up this phase switch, which is going to the input of the transformer. Mm. And this is what it would have to do if I was sitting down at the desk with all these real parts. This is the same exact thing as sorting the wires to the parts. Next, I'm going to work on the pad. This is the phase, and then going to do the pad section, the -20. So if something was coming too hot in the input, you'd press the pad button and it would reduce the input that's going to that transformer, which should produce -20. First, I'm going to put a XLR connector, and this is the phantom power that I'm hooking up now. So this is a switch on the console that would supply 48 volts to power the condenser microphones. This is the 48 volt source, which is set to 48 volts DC. Next, gonna put in the function generator that we use to generate the test tones to test the equipment. And you'd have to do this in the real world. If I was in a lab, I'd be doing the exact same thing. The only difference with this, sometime in electronics, or when you're designing anything, you could make a mistake, and by making a mistake, it could be a very costly mistake. You could burn up parts that you have to replace. You have to keep soldering and unsoldering different value parts until in time you get the one that you need. And this save you from really making any kind of a mistake, because you could design it in the program here and test it just like you would on the bench with great accuracy. It's really limitless at what this program can do. I can do anywhere from a cell phone, could design a computer on it. It's limitless as to what it can do. As long as it can generate the parts, then the sky is the limit as to what it can do with this program. So I have the components hooked up. Let me put this XLR jack. And let's see, power supply is set up for 24 volts plus and 24 volts minus. oscilloscope. The oscilloscope is going to be monitoring different areas of the circuit. Going to be monitoring both inputs, both the non-inverting and the inverting side of the op amp. This is exactly how you'd wire it up in the real world. Nothing different. I'm going to change the color of the wire to something that we can identify the different traces by. And then the red is going to monitor the output of the preamp. Install this capacitor here, and this resistor at the ground, so that the amplifier does not oscillate. Okay, everything is hooked up. Let's fire this up and turn the switch on and see what happens. And again, this is if I was in the real world. Before I turn it on, let me set the scale of the oscilloscope. I'm going to use 1 volt scale AC for both the A and B scale. Well, no, I mean let's go down to 50 millivolts for the A and the B scale. 50 millivolts A and B scale, and the D scale, we're going to set this at 1 volt. Okay, so let's fire this up and see what we get. Change the time base. Alright, let me check this pad and see if this pad works. Okay, so this is the readout that we get in. Let me change this color of this trace from a brown to a red so we could see it better. So here we go. The red is representing the output from the preamp, and let's put a multimeter on it to see the decibels. So we're going to put the positive lead of the multimeter. Positive lead of the multimeter to the output transformer of the microphone pre. And put this side to ground, which is net 0. Set this in decibels, AC, and let's do a test to see what it's putting out. So it's at putting out 0 dB with a 31 millivolts. Let's check the pad switch and see if the pad work. And I should get minus 20 or near minus 20 when I click the pad. So this is going down to minus 19 dB, which is close, and without the pad it's at 0 dB. Now I'm going to hook up a test instrument to see how clean the output is. And with this instrument is used to test harmonic distortion from the amplifiers. It could be a power amp or a microphone preamp, and standard is what, 0.5 total harmonic distortion. If you add that much, then you can you pass. So let's run it and see what's our total harmonic distortion. Our total harmonic distortion is down to 0.01, which is very, very good. Let's see how far up I can go with this amplifier in decibels. If you notice, you'll see the red is getting larger. So let me adjust the scale to a 2-volt scale. So right now it's up to 8 dB. And let me turn up more gain. Let me go all the way to max. All the way to max. I have to be on a 10-volt scale. All the way to max. The preamp is putting out 22.7 dB, and look at the harmonic distortion. It's down to almost nothing. It's going down to 0.002, 0.0011. It has a 0 in front of it, and that's how clean this preamp is. It's way below the 0.5. Let's see what's going on here in this ear with the phase shift. If you notice, show you how the phase switch works. If you're looking at the waveform now, right, you'll see where this is up, this cycle is up, and this cycle is down. This cycle is up, this cycle is down, right? So this is outer phase. in phase and notice the direction of the lines. If you'll notice now that the both of them is running in the same direction, let me adjust this 50-volt scale and bring it a little closer. See, now it's in phase. Because of the transformer going through, we have about a 1 or 2 degree phase shift, which is not out of phase. uh, notice the direction that it's running. See, they're both running in the same direction. But when you click the switch, if you notice, it's reversed. Right? In phase and out of phase. And this is what the phase switch is. And here is the phantom power for 48 volts. Let's see the frequency response of this amplifier. This is an instrument that we use to determine if the amplifier has good frequency response. And we're going to do a sweep from 20 to 20,000 cycles. Audio frequency is designed around 20 to 20,000 cycles flat. You have to be able to produce from 20 to 20,000 cycles in any audio equipment. Just a scale down in the megahertz. See, if I was building a transmitter or a cell phone, I could use this instrument because it's going all the way up into gigahertz. So going to the megahertz band. I'm probably going still in the kilohertz band and go to 50K. That's way above audio. Audio stop at 20 and starts at 20. So it's from 20K to 20, from 20 hertz to 20K. Let's run this and see what we get. We should get, if we're looking to get a straight line. go. So now I'm looking at the frequency response of the amplifier, and I've gotten it to be flattened out, which pretty much is what you want, is a straight line. So that's it for the uh, API microphone preamp. Now to build the printed circuit board, what I have to do, I have to transfer it to the other program that does the printed circuit board layout. And this really prevents you from making costly mistake. Now that I've verified and tested the circuit and know that it's working inside here, then I can go ahead and start exporting it to the printed circuit board layout. So I can build the printed circuit board. It exported all the parts to this program, and it locked all the critical parts like the transformer, the op amp, the input transformer, and this is the volume control, the pad, 48 volts phase, and the terminals for the XLR. Let's see here. Change this to a XLR. To an XLR connector. So this is the next part bin with all the parts. So just changes to two XLR connectors. I should put this one over here closer to the output transformer. This one over here to the input transformer. Lock both of them, and I'm going to tell it to put the parts in the best place for the board. Now it just finished routing the board and making all the connections to the printed circuit board, and this is the 3D view of the API microphone preamp, just like I would design it in the real world. These are all the parts: the input transformer, the op amp, the output transformer, and the XLR connectors. Now I'm ready to send this off to get the printed circuit boards manufactured. Let me show you a self-adjusting microphone preamp that I have designed. And it uses the API 2520 op amp. It uses the API 2520 op amp. This microphone preamp it's self-adjusting. So if sometimes singers, they get on the mic and they start to sing very, very low, a signal that represents a whisper. It's like 10 millivolts. And look what happens with this amplifier. It's going to self-adjust. So this is next to like a whisper, somebody barely whispering in the mic, right? And it's putting out an output voltage of 0.707. Well, within decibels, this is you don't have to pay attention to anything with a point anything because the human ear can only detect a 3 dB difference. Look what happens if I turn up like the person is singing louder or the person start to play louder in the play the, in the preamp. You find we're still getting the same output. And if I go from 70 millivolts to say 500 millivolts, right, it shoot up for less than a second. But look again, look at the output. The output is still zero. And if I carry it up to 700 millivolts, that's simulating the person shouting now in the microphone, right? You see, it goes up to less than a millisecond, but it comes back down and to zero. And if I keep turning up the preamp, which is simulating the person's either singing louder or the person playing the instrument louder, then we're still getting the same output. And if I go all the way up to 1 volt on this input, right, I'm still getting the same output as zero. Look what happens if I start to turn it down. If I'm turning it down, 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 it's still maintaining the same output as zero. Right, if I go all the way down to say 84 millivolts, you see it falls off and then it causes the output to maintain zero. So this is a self-adjusting mic pre that I designed. It have I can show you some of the parts inside of it. A RMS detector, the API input output, the balance output stage, there's a VU meter stage, light bar meter, see it went up to if you notice a light bar meter, wherever we calibrate and leave it, it's going to be staying there. Regulated power supply, regulated power supply for the phantom power. It has a stabilizer mode, or I could go into compressor limiter mode. It has threshold, it have attack time and release time. Right now it's in compressor mode, so if you notice, the waveform is down. It's down to -12 because I have it in compressor mode. So it's doing a gain reduction. And if I put the compressor out, you see where the waveform is clipping because it's not under control of the compressor. If I put the compressor back in, then you see it now start to regulate the output. And this is the printed circuit board for it. The op amp, servo amp, the output XLR stage, the power supply stage with a power transformer, the control compressor limiter stage. And these are the switches with the pad, mic line, the knee point, pad. These are the different areas of this printed circuit board, and this is what it looks like in a 3D view. This is what the circuit board look like. So I'll be sending this off to get the printed circuit board designed for this soon. Let me show you a high pass, low pass filter that I've designed. This is my high pass, low pass filter. Yeah, I purposely have this high pass here in this shape with the Q. It's adjustable Q. Let me go ahead and smoothen it out. Alright, and it can high pass or low pass. This is high pass, low pass mode, and I can adjust the frequency. It's voltage controlled high pass. As you see the frequency change and it went up. went all the way up to 7.5K on a high pass, and I could do a couple different shapes. Oh, what it? Let's try a band pass. This shape in the air in electronics that stand for band pass. Band pass. Notch frequency. This is a notch filter. It's in notch filter mode. Let me change the frequency of this. I can see it change in notch to this notch filter mode. And I can take it back out notch and put it in between high pass or low pass. Right now it's in the low pass mode. So I could have both sides of the filter doing both high pass or both high or low or vice versa. And now it's back in the high pass mode. This filter, it's switchable, and it has a slide sweepable with an adjustable Q. Design this one that I can change the Q to be sharp, and you'll see this get more spiky. As you can see the Q adjusted there. I find with this shape, I can, as a lot of the records that you have been mixing and you hear the high pass, when I configure it to this shape, a lot of people prefer it that way. This is this for the high pass, low pass filter. This is a fully parametric equalizer that I've designed, and it's a voltage controlled. And now that you all start using digital console, whenever you go to the EQ section, now you'll notice these shapes. The good thing with the digital consoles, you can look at it if you know the electronics, and it will give you better control over the console. Within the digital age, everybody's learning about bandwidth, Q, and so forth, and seeing a lot of these shapes now within the plugins and the test instrument. Let me run this EQ and show you some of the shapes. Right now with the bass section, I have it set to a wider bandwidth, and let me narrow down the bandwidth. And you see how narrow the bandwidth get on the bass. Now this EQ is a fifth order filter, and I could cut and boost up to 19 dBs. So the average EQ is plus and minus 12 or plus and minus 15. Like even on the SSL, is plus and minus 15 dB, and those are second order filters. I could even go beyond that point, which the higher the order of the filter, the better. And let's see what the boost is on this. Maximum boost is 29 dBs, almost 30 dBs. It's like a 6 order filter. That's in the boots. Let me let me flatten out the rest of these frequencies so I could check something here. Like in the middle, 50% is flat, just like you would on any EQ. So we should now see a straight line with only this, the bass boots. And this is fully parametric, so you could have, there's no anyone just from mid or anyone for bass. You could use any of them for anything. This is what it looks like. See here on this scale. Let me change the frequency and show you. See, the frequency changed. And let me widen the bandwidth. You see, I could get a bell out of this. I could actually go to a bell shape. Bandwidth got wide. Let me go real wide on the bandwidth. So bandwidth got wider. This is a really effective EQ. It's fully parametric. You can get all the different curves on it. See, I have a bell shape now. These are all the different shapes that I could get with this EQ that I have designed within the lab. Alright, and let me narrow this bandwidth now. with the shape here, I find that when I'm like EQing a kick drum, I could work miracles with it because you see, I can get all the shapes that I want. I could get all the different curves. So you go all the way to a bell. Thanks for watching. See you next time. Bye bye.